The area of a circle is pi r squared, and the circumference is the derivative of the area with respect to the radius. And there is a similar relationship between the volume and the surface area of a sphere. But that is not the case for any other shapes, like a cube. So what makes the sphere so special? Let's start off with a sphere of some radius. If we increase the radius by a small amount, how much would the volume change? The change in volume can be expressed as the difference between the volumes of the outer sphere and the inner sphere, where the outer radius is the original radius r plus dr. Now, we can expand this expression and cancel some terms out. The exact change in volume has quadratic and cubic terms with respect to dr. But if we make dr sufficiently small, then the quadratic and cubic terms become insignificantly small. Now, the quantity that we're interested in is the differential of v, which represents the local linear change in v with respect to a change in r. And there really is no surprise here. The yellow mass should approximately equal to the surface area times the small change in radius, which becomes a better approximation as dr gets really small. And this local linear rate of change is called, as you guessed it, the derivative. I use the language of differentials here for the sake of geometric intuition, but this essentially is the same as the limit definition of the derivative. Since we have differentials, we should probably attack it with some integrals. I use bright yellow letters here for dummy variables. And this tells us that if we add little volume elements up, then we should get the exact volume of the sphere. This radial symmetry is what allows this nice relationship between the volume and the surface area, so you could perform the exact same analysis on circle as well. Now, how far can we generalize this idea? Before we do that, let's introduce some new notations. Mathematicians would call the interior of a circle a two-dimensional ball, or simply just 2-ball for short, and the circle itself a one-dimensional sphere. In order to describe a circle in two-dimensional space, we need two parameters, a radius and a center. And it is the set of all points in two-dimensional Euclidean space such that the distance from the center is always a fixed radius. As for the ball, we change the equality to inequality to represent the set of all points that are within the radius. Now, if we don't specify the center, we will assume that the default parameter is the origin. And we will hide the radius as well, just to be lazy. Now, we can generalize this algebraic description to any dimension. So a n-dimensional ball is the set of all points in n-dimensional Euclidean space that are within a fixed radius from the center. And the sphere of one dimension less is the boundary of the ball. So the interior of the usual sphere in 3-dimension would be called the 3-ball. And the outer 2-dimensional shell would be called the 2-sphere. Now, let's define the generalized volume, which could refer to length, area, volume, or higher dimensional hypervolume, which depends on the dimension of the object. So the volume of a 2-ball is the area, and the volume of a 3-ball is the usual 3-dimensional volume. And we could apply the exact same reasoning to spheres as well. So the volume of a 1-dimensional sphere is the total length, and for 2-sphere, it's the area. Now, what about 1-ball and 0-sphere? Simply put, 1-ball is the set of all points on a line that satisfy this inequality, and more intuitively, the set of all points that are within the distance r from the center. So the one-dimensional volume, which is the length, is 2 times r. Now, the 0-sphere would be the boundary, which simply are the two endpoints. The derivative relation tells us that the volume should be 2. Zero-dimensional volume, also known as the counting measure, simply is the total count of all the points. So the relationship between the volume and its respective surface area holds for one dimension as well. Now, let's move up into higher dimensions, where visualization becomes nearly impossible. The most straightforward way to find the volume is to simply take an n-dimensional integral over the ball. And I use the dv here with the superscript to denote n-dimensional volume element. So for example, an area element can typically be expressed in Cartesian and polar coordinates, and the 3-dimensional volume element in Cartesian and spherical. There is a generalization of 2-dimensional polar coordinate and 3-dimensional spherical coordinate for higher dimensions, which we typically call hyperspherical coordinates. And you can use it to evaluate this integral, but I'm not going to do it in this video. But if you're interested, I will leave a couple of links in the description below. Now, we can isolate the radial part of this integral, then the integrand is n-1 dimensional surface integral, which is precisely the respective surface area. So the derivative relation should naturally hold for any higher dimension as well. Now, as for the actual volume, it can be expressed in terms of powers of the radius and pi. And the pi function in the denominator is the analytic continuation of the factorial, allowing it to work for any real number. Then, the respective surface area should be the derivative of the volume with respect to the radius. Now, if you look up the formula online, you will probably find it written in terms of the gamma function, which is the version of the continuous factorial function shifted by one step, and I personally don't like it. And this is the formula for the surface area you will find online. But it's hard to see the derivative relation in this common form. So let's start with n over the factorial of n over 2. Then, the factorial of any number is that number multiplied by the factorial of that number minus 1. Then, we can cancel out n and move 2 to the numerator. And lastly, rewrite this in terms of the shifted factorial function. Now, let's see what the volumes and the surface areas are for some lower dimensional balls and spheres beyond dimension 3. Higher dimensional geometry is incredibly difficult in general, but some nice properties that work in lower dimension, such as being able to abuse radial symmetry, works even in higher dimensions. For all intents and purposes, we covered everything we set out to solve. But if you're a math nerd like me, you might want to see how far we can generalize this result. Perhaps, this formula can work for any positive real numbers. Let's make a slight variation to our question to make it even more useful. Suppose we have any function f that is radially symmetric. Then, for any positive integer dimension d, the spherical integral of f is the same as integrating f over each little spherical shell. And if f is constant, this simply is the relationship between the volume and the respective surface area. So, does this integral relationship hold for any real number dimensions? In this paper that introduces quantum field theory in fractional dimension, Nobel Prize-winning physicist Kenneth Wilson conjectured that it indeed is true. More formally, the conjecture can be stated like this. The right-hand side is the spherical integral formula with respect to the radius, and the left side is the integral with respect to the Hausdorff measure of d non-integer dimension, which is, roughly speaking, a generalization of Lebesgue integral to work over fractals which has fractional dimensions. So, does this conjecture hold? Well, unlike integer dimensional space, fractional dimensional space is not very well defined. So, it's not impossible to construct a consistent definition of what a fractional space is so that the statement is true. But in general, it is false. If we use the construction outlined in this paper by Kakani, the conjecture is false. Perhaps, this is where the video should have stopped, but we got a sneak peek into some modern mathematical physics. Fractal spacetime is a non-mainstream theory devised as a model for quantum field theory and quantum gravity. And the mathematical formalism, newly invented to answer questions in physics, provides a solid framework to tackle nonsensical questions, such as the volume of a 1.7-dimensional sphere.